What specific problem does the RISE algorithm aim to solve in the context of large language models? And what key challenges does it address that existing methods do not?
The RISE algorithm aims to solve the problem of enabling large language models, LLMs, to improve their responses over multiple sequential attempts at a given prompt, particularly in complex reasoning tasks. A key challenge it addresses is the inability of existing models to effectively self-correct their mistakes during these attempts, as many models can provide plausible responses but fail to utilize their own prior outputs to enhance future attempts. Existing methods often rely on external supervision or do not adequately capture the iterative nature of self-improvement, leading to suboptimal performance. RISE introduces a structured approach that involves converting single-turn problems into a multi-turn Markov decision process, MDP, allowing the model to learn from its own responses and mistakes iteratively. This method not only enhances the model's ability to self-improve, but also generalizes well to out-of-distribution prompts, a capability that prior techniques have struggled to achieve.
How does the proposed RISE method work? Please illustrate the algorithm step by step, explaining the process of converting problems into a multi-turn MDP and how the data collection for self-improvement is structured.
The RISE method operates by converting single-turn problems into a multi-turn Markov decision process, MDP, to facilitate self-improvement in language models. The first step involves constructing an MDP from a dataset of prompts and their corresponding oracle responses, where each initial state represents a prompt, and the model's output response is treated as an action. The next state is formed by concatenating the previous state with the model's action and an introspection prompt that encourages the model to reflect on its response. For data collection, RISE generates multiple sequential attempts for each problem, ensuring that the data illustrates the learner's likely mistakes and how to improve upon them. This involves two strategies. The first is querying a more capable model for improved responses, distillation, while the second involves sampling multiple responses from the learner itself and selecting the best one based on associated reward values, self-distillation. This structured approach allows RISE to effectively teach the model how to enhance its responses over multiple turns, leveraging both successful and unsuccessful rollouts for fine-tuning.
What are the practical advantages of using RISE over traditional prompting or single-turn approaches? Discuss any specific improvements in efficiency, accuracy, or generalization capabilities that RISE provides.
The RISE algorithm offers significant practical advantages over traditional prompting and single-turn approaches by enabling large language models, LLMs, to improve their responses through iterative self-correction across multiple turns. Specifically, RISE enhances accuracy, as evidenced by substantial performance improvements on datasets like GSM-8K and Math, where models trained with RISE achieved up to 23.9% improvement over 5 turns, compared to only 4.6% for GPT 3.5. This iterative self-improvement capability allows models to learn from their mistakes in real time, leading to a more nuanced understanding of complex prompts and better decision-making. Additionally, RISE demonstrates strong generalization capabilities, as models trained on one dataset can still improve performance on out-of-distribution prompts, indicating that the self-improvement strategies learned are transferable across different problem domains. Overall, RISE's design fosters a more efficient learning process by leveraging on-policy rollouts and reward-weighted regression, which collectively enhance the model's ability to adapt and refine its responses dynamically.
How was the effectiveness of RISE validated in the experiments? Explain the datasets used, the experimental design, and the metrics employed to assess the performance of the model.
The effectiveness of RISE was validated through experiments on the GSM-8K and Math datasets, focusing on its ability to improve the performance of language models over multiple sequential attempts. The experimental design involved comparing RISE against several baseline approaches, including self-refined, GLOR, and self-consistency, while ensuring that the models were of similar size for fair comparison. Performance metrics included the improvement in accuracy over 5 turns, evaluated both with and without oracle feedback, specifically using metrics like MAJ at 1 and MAJ at k to assess the correctness of responses at each turn. Results showed that RISE consistently outperformed other methods, achieving significant performance gains, such as a 17.7% improvement for Llama 2-7B on GSM-8K over 5 turns, demonstrating its capability to enhance self-improvement in LLMs. Additionally, the experiments included ablation studies to understand the impact of different data compositions and iterative training on the model's performance.
What notable results were achieved with RISE when tested on datasets like GSM-8K and Math? Provide specific performance metrics that highlight the improvements made over existing models and methods.
The RISE algorithm demonstrated significant improvements on the GSM-8K dataset, achieving an 8.2% performance increase for Llama 3-8B and A6% increase for Mistral 7B, while Llama 2-7B saw a remarkable 17.7% improvement over 5 turns. In contrast, GPT 3.5 only improved by 4.6% over the same number of turns. On the Math dataset, RISE improved Llama 2-7B by 4.6% and Mistral 7B by 11.1% across 5 turns. These results indicate that RISE not only enhances the self-improvement capabilities of LLMs, but also outperforms existing models and methods, such as Self-Refine and Glore, which showed much lower performance gains. Overall, RISE's ability to instill self-improvement capabilities in LLMs is evidenced by these notable performance metrics across challenging reasoning tasks.
What are the key limitations of the RISE approach, and what areas for future work do the authors suggest to address these limitations?
The key limitations of the RISE approach include computational constraints that prevent more than 2 iterations of training, and the inability to perform more than 1 iteration when supervision comes from the learner itself. The authors suggest that improving self-generated supervision will likely require additional computation and iterations, indicating a need for a more efficient online variant of RISE to scale on-policy learning effectively. They also highlight the potential for integrating RISE's data protocols into general instruction tuning and post-training pipelines, which could enhance sequential self-improvement capabilities across various tasks. Furthermore, the authors note that while RISE has shown significant improvements, it currently fine-tunes models on one task at a time, suggesting that future work could explore multitask training to leverage the benefits of RISE more broadly. Overall, the authors emphasize the importance of addressing these limitations to enhance the scalability and applicability of the RISE framework.